This diagram outlines three major engineering challenges: the trapping of atmospheric heat by greenhouse gases, the structural integrity of synthetic polymers, and the non-radiative decay of OLED screens. On the surface, these operate in distinct fields of macroscopic science, yet they all shared the exact same physical driver: the rapid, sub-nanometer vibration of chemical bonds. The problem is that these atomic motions exist purely on the quantum scale. They are completely invisible to direct optical observation. To understand and manipulate macroscopic materials, we have to deduce their invisible quantum mechanics using spectroscopic data. This requires a three-step analytical process. We build a quantum mechanical model from first principles, correct that model for physical limitations, and then translate the mechanics into specific interactions with light. Decoding a molecular fingerprint is the act of reverse engineering the hidden physical properties of the world. This diagram shows the simplest conceptual model for a diatomic molecule. We treat the chemical bond as a tiny, idealized mechanical spring. Two primary variables dictate this natural frequency: the bond's stiffness, known as force constant K, and the reduced mass of the two atoms, represented by mu. These variables operate in strict opposition. Increased stiffness drives frequency up, while heavier mass drives it down. Hydrogen fluoride vibrates at a remarkably high frequency because the hydrogen atom is incredibly light and the HF bond is rigid. By contrast, an iodine chloride molecule, composed of heavy atoms with a weaker bond, vibrates at a much lower frequency. Because this is a quantum system, the energy of this vibration cannot increase in a continuous sweep. The molecule can only absorb or release energy in strict quantized steps. This chart shows the idealized rule of the quantum harmonic oscillator. Inside this symmetrical parabolic potential well, the allowed vibrational energy levels, from V equals 0 up to V equals 3, are perfectly and equally spaced. Even at absolute zero, the lowest energy state is not completely still. Heisenberg's uncertainty principle forbids classical perfect stillness, meaning a molecule always retains a baseline zero-point energy and continues to vibrate. The harmonic oscillator provides a clean mathematical baseline. However, the parabola extends infinitely upward, implying the spring can stretch forever without breaking, an impossibility in physical chemistry. This graph illustrates the critical flaw in the ideal model. Real chemical bonds do not stretch infinitely. As shown by the solid pink Morse potential curve, if atoms are pulled far enough apart, the bond breaks. The Morse potential serves as the necessary anharmonic correction, mapping the true physical boundaries of the molecular bond. Because of this asymmetrical shape, the energy spacing is no longer uniform. As vibrational energy increases, the energy levels progressively converge, getting closer together. At the exact threshold where the curve goes completely flat, the molecule hits its dissociation energy. The bond separates completely. This anharmonicity creates a secondary consequence. Transitions that skip multiple energy levels simultaneously, such as a jump of 2 or 3 steps, become physically possible. Here we see a matrix comparing these transitions. The single-step jumps are fundamental transitions, while the multi-step jumps allowed by the anharmonic model are defined as overtone transitions. While these overtones occur in the real world, the probability of them happening is low, making them much weaker to observe than fundamental transitions. The anharmonic model is essential. It aligns the pristine mathematics of quantum mechanics with the breakable reality of actual chemistry. Establishing these energy levels allows us to measure them by observing how the molecule absorbs infrared light. This diagram outlines the specific gateway rule for infrared absorption. To absorb an infrared photon, the molecule's vibration must change its dipole moment. The vibration must physically alter the charge distribution so that the oscillating electric field of the light has a changing dipole to grab onto. Heteronuclear molecules like hydrogen chloride and carbon monoxide are highly IR active. Their naturally asymmetrical charge distribution oscillates prominently during stretching. This creates a major blind spot for IR spectroscopy when it comes to perfectly symmetrical homonuclear molecules like nitrogen gas and oxygen gas. Because the two atoms are identical, stretching the bond does not shift the center of charge. With no changing dipole, these symmetrical molecules are completely invisible to standard infrared absorption. Relying purely on dipole interactions leaves us blind to a massive category of molecules, requiring us to use a second observational method. The quantum workaround for symmetrical molecules is a process called vibrational Raman scattering. This chart illustrates the difference. The molecule scatters the incident photon. Raman activity requires a change in polarizability. During Stokes scattering, the molecule steals energy, resulting in a scattered photon with less energy. In anti-Stokes, it donates energy, resulting in a higher energy photon. This decision matrix highlights the exact divide. Where infrared spectroscopy is completely blind to homonuclear molecules, Raman spectroscopy makes them clearly visible. Infrared and Raman are complementary techniques. They provide the dual lens required to fully map molecular structures across all symmetry types. There is a final layer of physical complexity. In the gas phase, molecules rarely just vibrate. They change their vibration and rotation simultaneously. This graphic reveals the reality. Instead of a single clean absorption peak representing an isolated vibration, real-world data resolves into a complex microview of closely spaced rotational lines. This is governed by a dual selection rule. The vibrational state must change by one step, while the rotational state must simultaneously jump exactly one step up or one step down. The P branch, shown in blue, represents instances where the molecule stretches but slows its rotation, requiring less photon energy. The R branch, in yellow, occurs when it stretches and speeds up rotation, requiring more energy. The notable gap in the dead center corresponds to a pure vibrational transition with zero rotational change, a transition that is physically forbidden for simple diatomic gases. Looking closely, the spacing between these individual spectral lines is not perfectly uniform. The gap between them narrows as they move outward. This text details the rotational penalty causing that shift. As a molecule vibrates at higher energy states, its average bond length increases. Because the radius of the molecule is now larger, its moment of inertia goes up, which mathematically forces its rotational constant to decrease. The precise spacing of these lines gives us the variables we need to reverse engineer bond lengths and moments of inertia from a single spectrum. This flowchart summarizes the entire analytical journey. We start with the idealized harmonic blueprint, apply the anharmonic correction for true chemical limits, and use infrared Raman observations to capture the physical reality. This pipeline systematically converts invisible quantum motions into highly structured, definitive data points. This text lists the results. From these complex spectra, we extract exact bond lengths, precise force constants, and critical isotope shifts. These documents show the real-world utility of that data. Vibrational parameters dictate the non-radiative decay, causing energy loss in OED electronics, and they map exactly how greenhouse gases trap atmospheric heat. This final conclusion captures the stakes. Vibrational spectroscopy allows us to identify exact molecular structures, giving us the incredible tools to analyze and engineer the vast flow of energy that